I'll be presenting our paper on the feasibility of 3D model-based forensic height and weight estimation. I am Nirja Thakkar, and this is joint work with Farid. Forensic science plays a critical role in holding criminals accountable, and perhaps more importantly, ensuring that the innocent are not wrongly accused. More than a decade ago, the National Academy of Science published a scathing report calling for an overhaul of how forensic techniques are validated and used. They found that with the exception of nuclear DNA analysis, no forensic method has been rigorously shown to have the capacity to consistently and with a high degree of certainty demonstrate a connection between evidence and a specific individual or source. A decade later, one of the original authors of the report concluded that we are still struggling with the inability of courts to assess the efficacy of forensic evidence. Here we will focus on the reliability of making the most basic measurements of height and weight from a single surveillance image. Even these seemingly straightforward measurements can be challenging for a number of reasons. There's an inherent loss of information when projecting from a 3D scene to a 2D image. With no reference measurements in the scene, estimating absolute scale is made even more difficult. Clothing, headwear, and shoes further complicate height and weight estimation, as well as basic human physiology. A person's height can change by 1.9 centimeters during the day. And pose and movement can result in big differences in apparent height. For example, when a person simply walks, their apparent height can change by as much as 6 centimeters. In this work, we will address this pose problem as well as the scale ambiguity problem. In order to address the pose problem, we fit an articulated 3D model to a single photo. By reposing this 3D model in a neutral pose, we can then measure upright height. Shown here, for example, is a person walking, and here is the overlaid 3D model fitted using the technique described in Pavlakos et al. And here's the 3D model reposed into a neutral pose. Even here, you can see the difference in the apparent height between the walking and upright poses. This modeling estimates a metric 3D model in real-world units, so height and weight can be metrically estimated. To begin, we created a dataset of 3D models with varying body shapes and poses. Here you see one body shape with neutral poses along the top and action poses on the bottom. And here you see one of the poses rendered with varying camera angles. We will compare our height and weight estimation errors to the simplest baseline, that of guessing a gender-specific height and weight. Using US-based adult height and weight statistics, we determined that guessing a gender-specific average leads to an average height error of 3.5% and a weight error of 18.7%. Our average height and weight estimation errors across all poses and all camera angles are 12.4% and 26.9%. Although qualitatively we saw good pose estimates to a single image, the metric scale estimate tied to the 3D modeling is not accurate enough to yield reliable height and weight estimates. To attempt to better resolve the scale ambiguity, we use the human interpupillary distance, a measure which has a relatively small standard deviation within adult genders. Using IPD to resolve the scale ambiguity, the height estimation error for neutral body poses and camera angles is 2.7%, significantly reduced from the previous 12.4%, and better than guessing. As the camera angle becomes more extreme, the errors increase. Here, for example, the average height estimation error increases from 2.7% to 5.3%, corresponding to plus or minus 4.5 centimeters. Weight estimation, even with the improved IPD scale disambiguation, is significantly worse than guessing a gender-specific average weight. The reason for this is that although the 3D modeling accurately captures the underlying pose, it is not able to capture non-average body shapes. In addition to these simulations, we evaluated the accuracy of height estimation on 800 in the wild images from the IMDb 23K dataset. There were some complexities to this analysis described in our paper, but overall, the average error for height estimation on neutral poses is 3.9%, not too far from the simulation error for neutral poses of 2.7%, but similar to guessing a gender-specific height. As I will describe next, we are working on improving the scale disambiguation with the goal of further improving height and weight estimation. While our method helps overcome the challenges faced by non-neutral poses, there still are advantages to classic single-view metrology methods that use techniques from projective geometry to incorporate known reference measurements. We are currently working to integrate these single-view metrology techniques, as well as extending the 3D model fitting with the goal of achieving more accurate height and weight forensic measurements, and perhaps more importantly, understanding the limits of these forensic techniques. Thank you.